So updates since last time. So I was pretty satisfied at the time with the performance I was getting. I don't remember exactly what it was, a couple hundred milliseconds for all primes less than 100 million or something like that. Double-digit milliseconds. And then I felt really stupid because I was still using brute forcing. So rather than some much smarter algorithm, so I switched those up and used sieve of Erasthenes, and I was able to get extremely low run times, which was cool for cutting out even numbers and using a sieve where I was able to find all primes less than 500 million in 55 milliseconds on the cluster. So I know I talked about trying some other problem sets, compression, video rendering, ray tracing, whatever, all of the generic, embarrassingly parallel projects are that people suggest, that ChatGPT suggests, but I kind of wanted to drill down on this one particular problem for a minute. Kind of curious to know, well, primarily, if the runtime disparity between a cluster and a laptop remains the same as you progressively increase the data size. And the TLDR is no, it does not stay the same, which I was kind of surprised by. So for all primes less than 500,000 was 55 milliseconds. For the cluster, 180 milliseconds, so 3 times faster for all primes less than 500 million. Still pretty considerable, once again, given that we're dealing with the same number of cores, and we're dealing with the same amount of RAM. That's not always the case, though. So I doubled that, and I said, okay, find me all primes less than 1 billion, with a B. The cluster took 329 milliseconds. The laptop took 513. So at that point, for 1 billion, all primes less than 1 billion, the cluster is still 35% faster. Okay. It's in line what I would expect at this point. Then I doubled it to 2 billion. At which point, the cluster takes 1.5 seconds to find all primes less than 2 billion. And the laptop takes nearly 2 seconds, 1.98. So at this point, the cluster is still 25% faster. Again, in line with what I would expect at this point. And the same can be said for upping it to 3 billion. It's 45% faster on the cluster than the laptop. And then it gets interesting. So for 4 billion with a B, on the cluster, that's 4.87 seconds. And on the laptop, that's 4.69. So this is the point at which, or somewhere around here, is the point at which the cluster actually becomes slower. And it becomes increasingly slow after that. So the disparity is gone from the cluster being ahead, and then that disparity has decreased until it's been flipped upside down. And then it continues to be flipped upside down because the cluster continues to get slower against the laptop. And so the last one I did was 5 billion. That was 0.3 of a second slower on the cluster. So there's kind of like a lot to unpack and a lot to figure out and a lot to learn. I feel like I've said that a few times with respect to MPI. And it's hard to say what that can be attributed to. I mean, Go is already optimized. The algorithm is pretty well optimized. Is it, could it be a matter of RAM speed? Maybe. Could it be a matter of RAM, intercore communication? Maybe. The amount of caching that happens on the CPU, maybe. It's hard to say. This is getting very deeply into this kind of problem set. Because at first I was convinced that the cluster was faster because it wasn't being thermally throttled as much, which certainly could have been the case, given how Task Manager was acting when I ran it on the laptop locally. So I guess the short answer is I'm not certain. But I mean, at the end of the day, the laptop costs $2,000 for 16 cores, 32 gigs of RAM. The cluster costs $300 for the same specs, albeit a much older generation of CPU, but same specs, same clock speeds. It's still a compelling proposition, right? Because you could add one more node to the cluster for $60 to $80, and it's at that point it's going to certainly blow the laptop out of the water. But I mean, at the end of the day, the laptop costs $2,000 for 16 cores, 32 gigs of RAM. The cluster costs $300 for the same specs, albeit a much older generation of CPU, but same specs, same clock speeds. It's still a compelling proposition, right? Because you could add one more node to the cluster for $60 to $80, and it's at that point it's going to certainly blow the laptop out of the water. And you could probably increase it, make it even more performant with perhaps some faster RAM. I don't know that any of these problem sets ever pegged out the RAM. Each of these only has 8 gigs, but it doesn't take a lot of memory to store just integers, right? It's like I said, it's still compelling. You could still do a lot of heavy computation on a cluster, even if you were willing to spend $600 and have 8 nodes and have 30 some odd cores, 100 gigs of RAM. You could do some pretty wild stuff, some pretty heavy stuff that most modern computers, modern desktops that aren't like specifically HPC driven can do. So you could buy 6 clusters, honestly, rather than a laptop, in which case that would be insane. But obviously it's not as simple as plugging in another node. You have to install programs on it, and then you have to orchestrate the job effectively. It's not just, I've shared the scripts, they're in the GitHub. It's not as simple as, okay, install MPI, install Prime, or MPI and Python. No, share the load. Like, all of this has to be explicitly stated. Send this amount to this node, this amount to that node. If this node finishes before that node, send it some more work. Ensure, jobs aren't being spread across cores. Ensure they're not being spread across CPUs. All of this kind of stuff. So it takes a lot of orchestration, I guess, for lack of a better word, to get that stuff sorted out on the front end and to learn this stuff. Because like I've said several videos before, the learning curve isn't very tall, but it's quite steep, especially if you already come from a programming background. So it's still a compelling value proposition to build a 4 or 5 node cluster. I'm not going to do that. I'm not going to increase this any further. It kind of serves its purpose. Most of this was for learning, and then I'm probably going to put Kubernetes on it. Having another node, it's not going to make Kubernetes any different for me. I don't have any hobbies that are very computationally intensive. So that doesn't make sense for me to add more nodes. So at the end of the day, I would still suggest building a cluster if you have the money, and particularly if you have the interest in MPI and distributed computing, and if you are interested in tasks that are embarrassingly parallel or extremely parallelizable. That's a terrible word. It's still a great learning process. It's still super cool to get really low run times for extremely large data sets. It still kind of blows my mind finding all primes less than 500 million in less than 60 milliseconds. That's a literal blink of an eye. That's crazy. On budget, use secondhand, third-hand equipment. It's pretty cool. It definitely served its purpose for me, and it definitely serves a purpose in general for budget, high-performance computing. But of course, it comes with the MPI part of that problem, because it's if you had a really expensive high-performance machine, well, you just run the Python script. You wouldn't have to be concerned about which machine it's going to, which core on which machine it's going to, how you want to deal with parallel processes and multiprocessing or multi-threading and all this other stuff. But you could still, if you're willing, I guess the TLDR is, if you're willing to put in a little bit of effort into learning MPI and learning how to optimize a Python script for MPI, and you have problems that are very parallelizable, then a cluster could still be a great option. At the end of the day, it's been very interesting, very informative, and a good bit of fun. As once I got the hang of using SCP to get the script on to the master node, and then building the Go project on the master node and importing stuff and sending the run job to the nodes and then running the run job is pretty, it took maybe 2 or 3 minutes. If I wanted to make a small edit to the Go script, I make the edit, push it to master, push it to nodes, build the project, run it. It's very quick. So once you get, I guess what I'm trying to say is, once you get the hang of it, turnover is quite low. Our turnaround is quite low for making an edit and then running it again. You could probably automate it with some type of CI/CD. I don't know. For me, that's not worth it. I'm just using this to learn. But if I was like deploying a cluster or like a high performance cluster for some reason, I would probably use a pipeline of some kind, maybe Jenkins or something, or some GitHub Actions, probably both. Just to streamline that process so I could push to main, and then it would, all the stuff would happen. Rather than having to go through the effort and CLI and SSHing stuff, and then coming back to local and then back to SSH, etc. There's a lot of steps. They're not terrible steps, there's just quite a few of them. So yeah, hopefully this small journey was interesting. Once again, if you have questions about anything I've done or anything like that, feel free to drop them in the comments.